So also, these linearized gravitational fields are characterized by the way their wave functions in what unitary irreducible representation of the Poincare group their wave functions transform. And we looked in particular on the effect a rotation, a spatial rotation, has on these degrees of freedom associated with the polarization. With the polarization degrees of freedom of the fields. And we found that these, well, the wave function transforms with an overall factor, just like an exponential factor, which knows about the so-called helicity, which we already met in the transformation behavior in the classical case for the modes of the wave function. So the helicity now in the quantum theory became the eigenvalue of J3, so it's the angular momentum. And two things can happen. Either the particle's momentum is kind of along the direction of propagation, so this J3 component, or it's oriented in the opposite direction. Now, we also wrote then down the field F mu nu hat for linearized gravity in terms of the usual annihilation and creation operators. And these operators themselves, as usual, satisfy canonical commutation relations. And in principle, this is all kind of a particular instance of a type of construction which you have already met elsewhere in your QFT courses. Now, today I will first of all start by talking briefly about now how physical are these excitations, kind of these force carriers of the linearized gravitational fields, which by analogy with, say, photons in electrodynamics, well, we call gravitons. So we have kind of a similar idea, right, that gravitational forces, say, or between anything, but in particular, say, between two static masses, say, there is a force exchange. This is exactly mediated by these gravitons. Now, the question of how real a physical concept or a quantity these gravitons are has been raised by various people, but I want to single out Freeman Dyson, who is a very eminent quantum field theorist, and well, he's contributed also to many other fields. So he has posed since a number of years, well, he's known for his asking of subversive questions, so that it's even acknowledged in Wikipedia, I saw. So he asked, well, how real are these things? So can one actually detect single gravitons? And what he then at the same time wonders, why he gives an answer, a tentative answer, is that, well, maybe one cannot. And if one cannot, what does it mean? What does it imply? Of course, we are interested in the question of what would it imply for quantum gravity. Now, what is the reasoning? Of course, the reasoning, in a way, has to do, again, with the weakness of the gravitational field, on the one hand, and how adequate is this kind of particle picture if we now quantize the linearized gravitational field. Of course, that has to do with kind of weak fields classically. Maybe quantum effects you would, of course, if perhaps expect in situations where gravity is very strong, so where already kind of classically this would not be a good approximation. So then the question arises, is the quantum theory I build up on these linearized wave solutions, can that ever be a good, can ever a good and physical quantization come from that? Now, of course, one can try then to rephrase the question in a quantitative way. Yes?
Can we get curvature of space-time out of gravity?
Oh, yes, of course. You see, because you see the way we introduce them, these F menus, they are just entries in the 4x4, the metric tensor.
But well, the way we did is like just the perturbation in the flat space and
Yeah. But you know, of course, how to compute curvatures. Curvatures tend to be certain, second-order derivatives of the entries of the G mu tensor, right? And now in this linearized approximation, you write G mu as 1 plus these F menus. And you can, of course, compute curvatures, and you will then get definite expressions of these curvatures as a function of the F menus. So that's straightforward, and this you would call curvature or linearized curvature.
Excuse me?
Yes?
Why we can require this perturbation field Lorentz invariant?
No, there was already a question. Yesterday, you have to be careful, although it looks like a tensor, if you have already made certain gauge choices. So you said, I look only at the transverse traceless modes, then that description itself is not immediately Lorentz invariant. But you can take care of that in an appropriate way. Of course, it comes from a Lorentz invariant theory. But there was already a question that was asked yesterday. If you want to have more information about it, just come maybe to me after the lecture. So getting back to the question of the single gravitons, of course, if you saw one, well, that would be, or if you had an experiment that, where we could just see single gravitons, well, that would settle the question. So the issue is, to start with, can I think up such experiments? And could I, even in principle, build them and make such a measurement? And of course, you're thinking of, gravitational analog, say, of something like emission of a photon electric effect, but now for gravitons. So in principle, you have a framework. You have already a framework from, say, QED, perturbative QED, and you can just see, well, what of these things would go through for gravity, and is it possible to detect single gravitons? So there are a couple of people who, inspired by Dyson's question, said about trying to make this quantitative. Putting just some numbers, attaching some numbers to this, and asking themselves, well, what would such a detector, what kind of properties would such a detector need to have? And how sensitive, how big, etc., would it have to be? So that is kind of make a first rough estimate of what it would require. Now, to start with, of course, you can say, well, we have already these gravitational wave detectors that are standing there, and I can think of these gravitational waves perhaps as coherent states of gravitons, if such a picture makes sense. So is there at any stage, if I estimate kind of how many gravitons are contained, say, in a given gravitational wave that reaches the Earth state, knowing kind of course, what the energy is, what the wavelength is, therefore, and what the strength of the signal is of various putative gravitational wave that reach us from specific sources, say supernova, can I come up with an estimate of, how many gravitons are in there? Is it very, very many, or am I already close to some limit, where I can start thinking about, oh, this is just a bunch of, whatever, 10 or maybe 100 or something. Now, if one does that, if one does make such a calculation, an estimate, one reaches a conclusion that a typical gravitational wave, which we expect to be able soon, hopefully, to detect here on Earth, these are very, very weak signals, as I already mentioned to you yesterday. So they have kind of an amplitude of around 10 to the minus 20. A typical, say it comes from a supernova, typical frequency is something like 1 kilohertz or 1,000 hertz, and associated wavelength is on the order of 3 times 10 to the 5 meters. So you can work out what's the expected graviton density is, of course, associating with a graviton an energy h bar omega, where this is omega. And the number you get is kind of a graviton number density. And an appropriate reference volume, three-dimensional reference volume, is just the wavelengths cubed. Right? So what you find here is 10 to the 37, and these are just rough numbers, divided by lambda cubed. And if you want, and this lambda is of course very large, if you want to see what this is in more intuitive units, it's still 3 times 10 to the 14 per cubic centimeter. So you see this is kind of, these are gigantic numbers. Yeah?
So the amplitude, what is the unit for the amplitude?
It's dimensionless. I mean, compared to, like the metric entries, you kind of say F mu. Yes?
The frequency of the graviton, is this something you calculate theoretically?
The frequency, yes, because it propagates at the speed of light. So, I mean, okay, so that frequency, well, that depends on the source. So now I said, well, this is kind of reaching us from a supernova or so. There are, as a matter of principle, I mean, gravitational waves occur over a very wide range of frequencies. And it depends entirely on where they come from, how big this is. This is something typical.
I mean, if we detect some frequency like this, how do we know that this is graviton, not something else?
Well, you look just, of course, it has characteristic, as we said, it characteristically deforms shapes in the direction of the propagation. So it acts on test masses. And of course, exactly this is what is used in this laser interferometers. I mean, there are other things, you have like bars, and under the influence of a gravitational wave, they will just change their length ever so slightly. So, and that is just due to gravity. I mean, that's just a prediction of Einstein's theory. So there are wavelengths of much lower frequency. So, for example, if you look at kind of stochastic background gravitons that would reach us, I mean, very, very old radiation, then this would be lower frequency. And then one can also lower these graviton densities somewhat. Of course, we haven't seen any of these things because they are just so extremely weak. But this just gives you an idea that one is extremely far away from being able to claim, well, we are looking at processes that involve just, a handful of gravitons. We are very, very far from this. Now to the question of these detectors. So the people who have looked into this are Bone and Rothman in a couple of papers. And I'm not sure, but we can easily put the references on the wiki. Here, this is one of them. Can gravitons be detected? So that's a paper from 2006. So they asked this question about the detector, and they made very kind of weak general assumptions that they want to be in place. For example, they want to have a detector, and they want to have it such that whatever the signals they are looking for would produce at least like one click in the lifetime of the universe. So that seems a relatively mild assumption, but also, I would say, a necessary assumption. Now, there are various things one has to be careful with. So it turns out, because gravity is so weak, you need very large detectors. But you have to be careful not to make them too large so they don't collapse under their own gravity. And that gives you a size that's known, of course, already, that it shouldn't be larger than about the mass of Jupiter. Now, that sets already an interesting scale, right? Then they take this as kind of the largest size for a detector. I mean, how practical this is another question. they assume there is just no noise, so you just see cleanly, just your gravitons zooming by. And also that your detector is 100% efficient. So totally unrealistic assumptions. Under this, they can show kind of as a Gedanken experiment, yes, that you might actually detect some gravitons. Now, once they make more realistic assumptions, namely that obviously the detector will not be 100% efficient, there will be lots of noise. So neutrinos, for example, are will be one very significant source of noise, for example. If you put in those things, then they say, well, then there are no realistic detectors which would ever serve this purpose. So they say, so they make the statement, they cannot see any fundamental reason why, they cannot come up with any, why it shouldn't be possible to detect single gravitons in some way. But clearly, if you put in any realistic numbers of what it would take, building such a detector for single gravitons, it's just out of the question. It just doesn't seem to exist.
I don't understand why neutrinos would become a noise when you want to detect gravitons.
Why?
The neutrinos may become a noise when you want to
Yeah, well, of course, they are a source of mass and energy also.
Oh.
Right. Like everything else. So that's maybe then a drawback, again, of talking about gravity. Now, they then turn to a slightly different question, which is to say, what are sources of gravitons, of single gravitons? And then, one of the things you can consider, that has actually been considered already back in the 70s of last century, is, for example, to say, well, spontaneous emission could just take place. Just take, say, an excited state of hydrogen, say, and can you compute the transition rate for, say, a graviton being emitted? A graviton is just a quantum of energy. Of course, usually we think of course, photons being emitted, but just as well, in principle, it could just radiate out a graviton and then, fall onto a lower energy level. So one can compute the transition rate of such a process. So for a hydrogen atom, to undergo spontaneous emission of a graviton and go from the level 3 D2 under emission of a graviton, single graviton, to a lower shell, 1s, and so spontaneous emission, that is, and you find that there is a transition rate of 5.7 times 10 to the minus 40 second. So there is a well-defined computation you can make. It turns out that Steven Weinberg, who quoted this result in his book, his famous book from the 70s on general relativity, got it slightly wrong because he put in some wrong wave function. But he was still right within a factor 2 or so. So this seems to be right and has been reproduced by other people. If you compare it to the transition rate for a photon for that same process, it is suppressed by a factor of 10 to the 47. Okay? So this is something you do not want to wait for to happen. Right? So it's clearly for all practical purposes, totally irrelevant. Yes?
Are there any feasible cosmological ways for gravitational wave detection?
Say that again?
Are there any feasible cosmological ways for gravitational wave detection, like looking at galaxies or
Yeah,
stars?
well, people speculate. For example, one source that's been speculated are what are they called? Primordial black holes. Might image such things, but of course, no one has seen it. We don't have any evidence that there are actually primordial black holes floating around in the universe.
No. But looking at some responsive stars or galaxies to passing gravitational waves, just that type of thing. Not for sources, but for detection.
Yeah, well, for single gravitons, I think there are not very many things people have come up with. Yeah, have a closer look. I think Bone and Rossman discuss some of these possible sources. They are all highly contrived. You know, this is maybe not contrived because, well, in the sense that it's kind of transparent, the process one wants to study here. But of course, when it comes to cosmological sources, well, everything is a bit floating up in the air, I would say. So this was the spontaneous emission rate. Now, and so combining these things, one comes to the conclusion that for all practical purposes, it's unclear that if they existed, they could be ever seen. I mean, the very likely answer is not. Could it perhaps be that there is something why they could not even be detected in principle? Well, perhaps yes. I mean, we haven't constructed any watertight argument for that, but this might be the case, and people have advances as an hypothesis. And for example, if you talk to Stephen Bone, he says, well, that means, so he doesn't believe that these gravitons can be detected, and he makes the conclusion that, well, clearly, therefore, gravity shouldn't be quantized. It seems to me that it's not something that immediately follows. It seems to me it's logically two different things. Even, say, if gravitons cannot be detected, are maybe not detectable in principle, that means they don't have really a physical reality beyond making some formal appearance in certain expressions you can calculate and are seemingly meaningful in QFT. It doesn't necessarily mean that there are no quantum gravity effects in the world and that quantum gravity per se doesn't exist. Right? It might exactly be that there are not useful concepts in the range of energies and scales where exactly you're looking, where quantum gravity effects are going to play a role. It could just be that they are completely useless. So in that sense, well, you could wonder about, you know, how relevant it is to compute, say, graviton scattering amplitude. I mean, you know, there are people who like doing such things. So clearly one has to take all of that with a grain of salt. But for me, the conclusion would be, if this were to be the case, that, well, it probably gives us a strong hint that just looking for gravitons and looking at processes involving gravitons is maybe not the most sensible thing to study when you're looking for a theory of quantum gravity. Okay, so that concludes this part of my discussion. And what I want to do now is to, well, we've understood, you know, what kind of excitations we are looking at, and let us now have a look on how to construct a gravitational path integral. So how to just go about with a standard quantization, now working with these linearized fields and their quantum analogs, and just construct a standard quantum theory and see what happens, and also then see what goes wrong. And of course, what goes wrong might very well be connected to the kinds of issues that we've just touched upon in this discussion about how real are gravitons. Okay, so this brings us to a discussion of the path integral. I very, very briefly recap some of the notions that bring us to the path integral. That's also done with the view of later on, I mean, now after having discussed this perturbative path integral, in week 3, we'll be coming back to non-perturbative implementations, because we'll see there are some tricky problems associated with the perturbative formulation. So what I just want to do is very, very quickly run through some of the logic behind setting up the path integral and build up also some geometric intuition, which will be very useful for us later on. Now, let's the field theoretic side of things, let us set this aside for the time being, but make a step back and look at quantum mechanical path integrals. So very quickly, how does one get there? Simplest examples are, of course, that of a non-relativistic particle in some potential, sufficiently simple potential, so that you can attack this problem. Now, how do you formulate quantum mechanics the path integral way? That's not usually the way it is taught in elementary quantum mechanics courses. There, you usually work with operator presentations. So let us briefly recap the difference, or one should say, the difference and complementary features of these two approaches. So we're talking about the non-relativistic particle. For the time being, very simple system. It is associated with a classical phase space. So let's say in 3D, could also do it in 1D just for simplicity. The classical phase space is spanned by 3 pairs of variables, xi, pi, I running from 1 to 3, which satisfy these elementary Poisson bracket relations. Xi Poisson commuted with Pj gives a delta Ij. And we had a one-dimensional version of this yesterday on the blackboard in connection with discussing the 1D harmonic oscillator, if you recall. Now, again, let us look at a simple dynamics for this. One term m x dot squared over 2 plus some potential which just depends on x, which I leave unspecified for the moment. Now, how does one proceed in canonical quantization? Our canonical quantization is putting heads on things, generically speaking. So that means associating self-adjoint operators, xi hat, pi hat, and h hat with the corresponding classical quantities.
So you're missing a square?
I'm missing a square.
X dot.
Oh, indeed. And all of these operators act on a Hilbert space that consists of square integral functions on R3, so that's the original, if you like, the original configuration space spanned by the 3 x's with respect to the measure dx. Now, the Poisson brackets get represented on this Hilbert space in the form of these commutator brackets, which are again proportional to delta ij, where now the h bar makes an appearance. And the nice thing is that you have an essentially, up to unitary equivalence, a unique representation of these algebraic relations. So that fixes simply what the quantum representation is for these. And that's then the standard, one way of writing it is as a standard Schrödinger type representation. Where xi hat becomes multiplication by xi. Let me write it like this, you know what I mean. Pi hat is represented by a partial derivative minus I h bar d by d x I. And consequently, just plugging this into the Hamiltonian, you get a form h bar squared minus h bar squared divided by 2m times nabla squared derivative operator plus e of x. And, well, again, let's assume that this is, reasonably nice. So this operator is also reasonably nice. And then what we try to do is to solve the Schrödinger equation. Which now, for this simple system, takes the form of an eigenvalue equation, h hat applied on a wave function, which lies in this Hilbert space of square integral functions, and solves the eigenvalue equation h psi equal to e psi. And of course, E then runs through all possible energy eigenvalues of the system. Is it too low? Can you not read it? Can you read it? Okay. So this, well, so good, so familiar. This is, of course, what one calls, the canonical way of quantizing, writing down eigenvalue equations for the Hamiltonian in particular. Of course, there might also be other operators whose eigenvalues I might be interested in, but this is, of course, the most important one. And then solves this equation. Now, yes?
How do you recover time dynamics?
Oh, it's trivial. It's just an exponential. It's just an exponential factor. Yeah. So this is, there's a time-independent Schrödinger equation already, which is applicable to this simple case. You split that off, of course, in the first step. Now, equivalently, and well, making time more explicit, you can formulate the dynamical equations for a slightly different set of objects, which of course amounts exactly to the same. You're solving the same problem, but it looks slightly different. And that concentrates on the unitary time evolution operator. Evolution operator. So I call this capital U. I don't put a head on it. People don't usually do that. Also, it is an operator, so it's basically the exponential of the Hamiltonian. Minus I h hat t minus t naught divided by h bar. And the fact that it factorizes in this neat way and only depends on the difference of the t's has to do with the fact that this is especially simple and problem without explicit time dependence in the Hamiltonian. Okay, what are my wave functions? So this is the wave function that has evolved already to the time t. I get it by applying this unitary evolution operator to the initial state, right? And psi of t naught. So this is how this object makes an appearance. Now, what more can I say about the quantum states? Of course, usually we will work in a specific basis, and here, well, usually one works in either of two bases, either the x or the p basis. But let us look at the position basis. Let us look at a bunch of position eigenstates. Which are those states which are eigenvectors of x, the operator x hat. So x hat, well, I write it with this vectorial thing, so there are three different components, of course. Applied to this eigenvector gives x multiplication by x. And of course, you are aware that these x's, of course, they're improper eigenvector. So they're not themselves square integral, but one deals with these things in the usual way. I mean, this is, after all, this is standard quantum mechanics. Now, I can write down a wave function, so in this explicit basis, as a function of x in t, by taking scalar product of a bra and a ket with the wave function that appeared down here. Now let us look at, let us now represent this wave function at time t. Let us substitute in this expression, so we get an explicit dependence on this evolution operator, capital U. So let me look at this for some different location x prime, say t. So this by the above is x prime, bra x prime, psi of t, and let me now for psi of t substitute in this expression here. U of t, t0, psi of t0. And let me slightly rewrite this by inserting a representation of the unit operator, a so-called resolution of unity, in between u and this psi of t0. Because this is an improper eigenbasis, I'll pick up an integration, a continuous integration over all intermediate states. Let me call those states x double prime. So this is the integral. Of course, if that was on R3, of course I get a threefold integral here. An x prime, u of t, t naught. Here I have now my resolution of unity, a ket and a bra, and my original wave function, psi of t naught. Now, this thing here is, using my earlier notation, is a wave function psi of x double prime at the initial time t0. And this here, by definition, this is the object kind of I am after. This is a so-called Feynman kernel or propagator. And it depends on x prime t and x double prime and t naught. So kind of an initial time and location and a final time and location. So this object G is called the propagator, or the Feynman kernel. It's really a Green's function here for this Schrödinger operator. Now, the interesting thing for us is that knowing this object or being able to compute this is the same as solving the dynamics. Right? And you see that it is, of course, everything is very closely related. So there is a conservation of information. Now, the interesting point for us is that this has a path integral representation. So I can write this object as a path integral. So I write down this path integral. So it's a sum over paths. So that brings in kind of a qualitatively new mathematical quantity. And then solving this path integral, well, is tantamount to constructing this propagator. And knowing this thing is, I have solved the dynamical problem for this simple quantum mechanical system. Okay, so for this guy, I have the following representation. x double prime e to the minus I. Now let me write out explicitly what this was in terms of the Hamiltonian operator T H hat. So now by T, I have now without loss of generality set T0 equal to 0. Anyway, it's a translation invariant system, so it doesn't make any difference, just for simplicity of notation. So this is the object I'm interested in. And the statement is that this can be now written as a path integral. Now, what is a path integral in this simple case? So this is a kind of a path integration with this curly d. That's my notation. And I say in a second what this is. E to the I divided by h bar s of x and, of x of t. Now, this is an integration. So x is now an entire path in x space, which is a function of t, subject to some boundary conditions. So I'm pinning down the path in some initial and some final location. That's one of the possible choices of boundary condition I can make, which is natural here. So say x at the time 0 is given by some initial point x, and x at the final time t is some point x prime. So that is the prescription. So I should integrate over all paths, and for each path in x space, I evaluate what its classical action is. And the action, here is the action, that corresponds to my original dynamics with this Hamiltonian up there. Okay, it came, of course, from some Lagrangian, right? And I computed for each path. So now one thing to notice, of course, these paths have nothing to do with solutions per se. They're just paths as a function of x, and you can evaluate the action on them. And you are instructed to do this integral, so to do this over all paths. Now, this is, of course, is a functional integral, because x is a function of t. And there are just so many, of course, there are infinitely many ways of choosing paths between two pinned down points. Okay, so it's a functional integral. So you say, oh, wait, this is not a priori usually well-defined unless, one is careful and specifies exactly boundary conditions, convergence properties. And one way of doing it for this very simple example is kind of a classic way of regularizing this expression to start with, then kind of removing, so basically hacking the path into little pieces, and then making, taking away the regulator. That means making the path, the regularization finer and finer until you are really describing continuum paths as you want to. And let me just remind you how this goes. Well, first of all, I should write down the the action for you. So the action depends, of course, on the entire path. So it's a functional. And of course, you get it by integrating from 0 to t, some integration parameter, time parameter t prime, the Lagrangian of the original system, which is m half x dot squared minus v of x. Okay, so Hamiltonian is, of course, kinetic plus potential energy. Lagrangian, as usual, is kinetic minus potential energy. Okay. Now, the canonical way of defining this path integral goes as follows. No, this is, this is a fixed, my background, this is my background blackboard. So we're getting this from a limiting process. Where, let me draw a little picture. So let this be kind of this stands for the x direction. So that is my initial condition. The path at time 0 is fixed to the point x. And this is now time going upwards. And this is my location at the final time, x at t, which by definition I said I would call x prime. Now, the way I'm getting to kind of the space of all continuous paths is by first considering a simpler class of paths, which are piecewise straight. So just instead of being arbitrary, continuous curves, I make them up from little pieces of straight line. So that's how I start out. I divide the time interval into equal steps, delta t, right, from one to the next. And I start by considering paths that link these 2 points, which are just piecewise straight. So here's an example. That's another example, etc. No, sorry, I should go to this point. So these are all examples of piecewise straight paths. Just a second. So this is, say, the point here, a point x of delta t. This is another point x of 2 delta t here, etc. for a given path. Yes, question?
Fall back on themselves.
No, they advance. No. Here are just things that advance in time. So what is my limiting process in the end? So the idea is to first make the computation by integrating over these types of paths, and then make the time division finer and finer. So that's what I meant by removing kind of the regulator. That's, of course, an intermediate step, and not what I want. So what is this delta t? It's given by definition, is characterized by this parameter n, which is just the number of slices in which I divide my original integral. Now, the limiting process consists in letting delta t equal to 0. And of course, it entails that n has to go to infinity. And I then perform the computation I want to perform. I integrate, from integrating over a particular class of paths, namely those that are piecewise straight. Consisting of capital N segments. Now, if you're interested, as I said, this is not usually covered by standard quantum mechanics courses, but if one is interested in this path integral construction, one is often referred to this book by Feynman and Hibbs, where this is done. And you find exactly this kind of a picture to construct this path integral. And of course, the point is here, well, now using just simple quantum mechanics, you can for sufficiently simple V, you can evaluate this in a number of steps. And this is perhaps also something you did in a QFT course. Yeah? Can I assume that is right? And what one finds, for example, is explicitly. So what is then, you're of course also interested, well, what is then this measure explicitly? Of course, this measure, using this limiting process, also appears as a limit. So it appears as a limit as, say, n goes to infinity, of a certain quantity, I mean, just ingredients you get from evaluating this exponential. And the various steps, you insert resolution of the identity, you insert a complete set of momentum eigenstates. Why? Because the kinetic term is, of course, will then just be is of course diagonal in that basis, and you can immediately evaluate this part of the exponential function. So as a result of all this, just to give you an idea, of the quantities that appear here, h bars delta t to the 3 n over 2, and then some intermediate, so a bunch of intermediate integrations that all come from really doing this insertion basically at every time step. So doing it n times. And I don't have the time to do this here, but it should be probably somewhere in your notes if you've ever done this. So there is a very explicit construction, so it's kind of a hands-on calculation in that sense. Now, two things I want to point out. Of course, we started off with this operator sandwich between x double prime and x, which is also from e to the I Hamiltonian times t. Of course, and you said, oh, but it's curious that the path integral, this continuum path integral description, ends up with having an exponential factor where the action appears upstairs. But of course, you can trace this exactly to evaluating this various, parts of the calculation. So this is just what happens if you do the explicit calculation. So the relevant quantity that now appears in the exponent is the original action, not the Hamiltonian. And that's, of course, a generic. So that's one of the remarks I wanted to make. Now, this is not terribly well defined for once, because what I'm writing down there, and what this thing here is not a real measure to start with, because it's complex valued. You can still make sense of that, because after all, we're only talking about Gaussian integration. So that's something that still can be done. If you want to do it in a clean way, you make an analytic continuation of this path integral, which makes the integrand, and therefore also the path integral measure, real. And of course, in the real domain, you then have clean ways of discussing the convergence or otherwise of whatever appears in the integrand. So that's another step that is also very often used in practice, and that the quantity you analytically continue in this simple problem is t. So from this t, you go to what is called Euclidean time, which is just differs by an imaginary I. And substituting this in, one can easily see, makes everything real. And of course, then one has to be careful. So if it's an analytic continuation, you can, of course, rotate back and forth happily, as long as you're not crossing any singularities. So that's, of course, also true for this type of analytic continuation. But this can be done in these simple cases without any problems. So you solve it in a mathematically well-defined way by analytically.
Question?
No, let me just write it down first. Continue to imaginary time tau equal to IT. Yes?
So you're saying that if we have a gravitational path integral, and for any manifold, we'll be able to switch between Euclidean and Lorentzian?
I haven't said anything of the kind. We're talking about quantum mechanics. And I'm telling you what the standard Wick rotation is in a non-relativistic setting where this T is clear, it's a Newtonian time. Yes. But you can already anticipate that clearly an issue will arise that in a theory where it's not necessarily, you don't have one, given time, if you want to play the same game, it might not be so straightforward what you mean by a Wick rotation. And that's, of course, exactly a problem that will come up and we'll discuss when we get to real gravity. For perturbative gravity, this will not be an issue because perturbative gravity lives on Minkowski space. And on Minkowski space, well, you also have a time, of course, and you can just basically continue in that time parameter exactly in the way given here. And there are well-defined axioms, the Osterwalder-Schrader axioms, that ensure you that if you compute the dynamics, the Green's functions, the endpoint functions of your quantum field theory, that you can analytically continue between Lorentzian and Euclidean signature. So there you have well-defined tools. So you just regard, of course, you should just regard it as a trick, So there is something, an amplitude you want to evaluate. You cannot really do it in the complex domain, or not easily. What you do is to just analytically continue it, do the calculation, and then rotate back. So in principle, and there is no physical deep meaning you attach to this Euclidean time or the system with Euclidean time. You should just think of it, usually as just a calculation trick that enables you to calculate an object which you're motivated to calculate within the Lorentzian theory. So that's the point of view we'll be taking for the time being. There are, for the simple quantum mechanical cases, these path integrals, again, given that the potential is not too nasty, they are mathematically rigorously definable. And you always do this in the Euclidean domain. And what you end up with in this construction is really a specific measure over a limiting set of paths. Namely, the paths you get by taking the limit as n goes to infinity. So this piecewise linear thing. So there is a well-defined continuum limit. And what you get are paths that are very non-classical in a way. They are nowhere differentiable. So these are, you can think of these as little random things, random walks, that just jump, between different points. Now, the question is it something mathematically well-defined? I get, taking this limit. The answer is yes, and what you get is a so-called Wiener measure. So that characterizes just a random process, and that appears in many, many, many places in physics. Just to point out to you, there is a perfectly well-defined kind of mass behind this, at least in the simple quantum mechanical cases. Of course, if you now start applying this to quantum field theory, and even to something like gravity, there's very little But in principle, there is a lot you understand what you would like to have just in analogy with these simple examples. And you see also here's a lot of geometry in there, in the path. What will happen in gravity is the paths that appear in the path integral, they will themselves be geometric higher dimensional objects, namely kind of histories of the universe. So a path will be a curved space-time, whereas here is just a path is just an embedded path in some fixed background. Now, so that in gravity, this is a preview. That's an infinitely more complicated thing, but its geometric nature is actually not so totally different. And one way of approximating these curved spacetimes will be, again, by approximating by things that are piecewise straight. Geometries that are also called piecewise flat. So in the same way, as here, instead of working with continuous paths, we work with these objects, you can do a very similar thing also with higher dimensional geometries by approximating them by things that have piecewise no structure with respect to gravity. So they are flat, piecewise flat, but they can have curvature, and this curvature will occur at the higher dimensional analogs, if you like, of these corners here for the embedded paths. Okay, that's where we'll be going, and I'll see you back tomorrow.